Hello, and welcome to Lecture 3 of Circular Motion in Phys 1104. In this video lecture, we're going to get a little more mathematical and develop some equations that are useful for describing the kinematics of circular motion. Let's start by briefly thinking about units for period and frequency. So in the first video lecture of this unit, we found the period, which is the time for one revolution of some kids on a merry-go-round, and that's just a time, so we can use seconds or any other units of time. And we found a frequency, which is a number of revolutions per unit time, and we expressed it in revolutions per second. But we should speak a little bit more about units for frequency. This came out 0.403 revolutions per second, right? Literally 0.4 revolutions per second would mean the child goes about 2/5 of the way around the circle each second. And a revolution per second is defined as a hertz. Really, a hertz is a repeated thing per second. So in circular motion, the thing that's being repeated is trips around the circle. And because a revolution isn't a unit, it's a thing you count, that'll often be written as just 1 over s, 1 over seconds, or seconds to the negative 1. Now, you're probably more familiar with RPM, which are actually really inconvenient units, right? But a physicist would write this as revolution per minute. That's what RPM stands for, and writing it this way makes it clearer that there's a numerator and a denominator. And so now you can see that usually you convert out of RPM because they're horrible units to work with, but if for some reason you wanted to put this frequency into RPM, you would just do the usual conversion fraction, where all we're doing is replacing our seconds with minutes. And if you wish, you could now carry out that multiplication. Something we can do that's very useful is that we can easily relate speed to period. Speed, as always, is a distance traveled per time taken. And note that the period is the time for one revolution. So if some object is going at a constant speed around a circle, then in one period, it goes a distance that is equal to the circumference of the circle. And so that's just 2 pi r over the period. And there we have a direct relationship between speed and period. And note that the period is 1 over the frequency. And so we can also write this as 2 pi r times the frequency. One thing we need to be able to do is go back and forth between angular variables, the angles theta, and arc length related variables, the distances traveled and speeds and so on of things moving around a circle. Let's see a very simple example, but then I'm going to show you why this isn't the way we should do it. So let's suppose we have a circle that's 300 meters. And let's say something started in one place and has gone 100 meters around the circle. Then it's gone 1/3 of the way around the circle, 1/3 of a turn. And so we know that the angle here has to be just 1/3 of a full circle, or 120 degrees. But now think if you didn't know the circumference, perhaps you know the radius. You can of course get the circumference, but that's a little calculation. And then you're going to have to use a factor of 2 pi in this conversion between an arc length to get to an angle. And there will also be the factor of 360 that we just did in our heads here. That's not really very convenient in general. So while we can work in degrees, it's really not all that convenient. There are factors of 2 pi and 360 that have to float around every time we're moving back and forth between angles and arc lengths if we do so. There's a far more convenient unit of angle to work in, and it's the radian, because a radian is defined as the number of radii that fit into the arc length. In other words, an angle in radians is defined as the corresponding arc length divided by the radius of the circle. I think an example makes it clearer what this means. Suppose we have a runner going around a circular track that's 100 meters in radius. If she runs 100 meters around the track, then she's gone through an angle of 1 radian. If she goes 200 meters, that is 2 radii, and so she has gone through an angle of 2 radians. And if she goes 250 meters, that's 2.5 radii, and so she's gone through an angle of 2.5 radians. One last thing to notice about it is that angles in radians are actually unitless. So even though we'll often write radian as if it's a unit, it really isn't. See, we have a length in meters divided by another length in meters, and so theta is clearly unitless. We'll often flip this relation around this way for convenience, and we're about to use it in this form a lot. That convenient definition of angle is going to lead to convenient ways of working with angular velocity as well. So let me just remind you of a convention. Positive angles are angles counterclockwise from the x-axis, and so by this definition, positive arc lengths are also measured counterclockwise from the x-axis. Now, our tangential velocity is just the rate of change of the arc length. It's how fast you're going along the length of the circle's circumference. And so it's simply this derivative. Notice that the speed is the magnitude, the absolute value of the tangential velocity. So you can think of tangential velocity as just speed with a plus indicating counterclockwise or a negative indicating clockwise. Now, we can substitute in this expression for s, realize that the radius is a constant, and so we just have this relationship for the tangential velocity. But d theta by dt is the angular velocity. And so this has now given us a nice simple relationship that lets us go back and forth between angular velocity and tangential velocity, which is closely related to speed. We can do exactly the same thing and look at tangential acceleration. Remember that in general we can divide the acceleration into a radial part and a tangential part. The tangential part is the one that changes speed. Well, technically it changes tangential velocity. There's a sign convention still. But it's simply the rate of change of tangential velocity. And so we can again substitute in our expression for tangential velocity and obtain this. And this derivative here is just the angular acceleration. And so now we have a simple relationship between tangential acceleration and angular acceleration. And look, we have a nice pattern that relates how we go from length-based variables, arc length, tangential velocity, and tangential acceleration, and the corresponding angle-based variables. So now I'm going to derive a very useful little formula that you've probably seen in earlier physics courses but don't know the origin of. I'm going to get the acceleration, the magnitude of acceleration of an object going around a circle at constant speed. So here's this object. It's gone through some angle theta. I'm going to add on to the diagram a displacement vector here, which I will call delta r. And I'm going to point out that because these velocity vectors are tangent to the circle, they have to be perpendicular to these gray radii. And the other thing I'm going to need is the definition of average acceleration, which is a change in velocity over change in time. And so the magnitude of the average acceleration is the magnitude of the change in velocity over change in time. So now I'm going to proceed using exactly the methods we know. I'm going to do a vector subtraction to get delta v. So there's my vf, and here's my negative vi. And so my change in velocity vector is right here. And now what I want to point out is that because these velocity vectors are perpendicular to these gray radii, this triangle that I just made out of the velocity vectors has to be a similar triangle to this triangle made out of the gray radii and the delta r vector. And so this angle here is theta. So, since those are similar triangles, the ratios of their sides are the same. So I'm going to say that the radius of this circle is capital R. And that equality of ratios tells me that delta R, that's the magnitude of that delta R vector over the radius of the circle, is the same as the magnitude delta V over VI or VF, but those are both just the same, right? This is going at uniform speed, and so that's just some speed V. Now, I'm going to make an approximation, because this delta R vector has a length that is similar to the length of this little arc here. So I'm going to point out that this arc, the length of this little piece of circle here, is some delta S. And that delta S is the speed times the time that it takes to go from this point to this point. And that's approximately the same as delta R. And so that means my delta V over V is approximately just V delta T over the radius of the circle. And so if I just rearrange that, I get delta V over delta t, that is the magnitude of our velocity, our change in velocity vector, is approximately v squared over r. Now, this is the magnitude of the acceleration. Now, at the moment, it's only approximately equal to v squared over r. But if I take the limit as theta gets very, very small, then the length of this displacement vector becomes equal to the length of that little arc. And so as theta goes to 0, this becomes precise, and the actual acceleration magnitude is in fact v squared over r, which is probably a formula you've seen before. So we've just derived for uniform circular motion that the magnitude of the acceleration is v squared over r. What about non-uniform circular motion? Note that in uniform circular motion, all you have is a radial component of acceleration. What about the radial component of acceleration in non-uniform circular motion? Well, it's difficult, and I'm not going to do it because the derivation is long, and I don't think it'll really help your understanding much. But we can show that the radial component of acceleration is still v squared over r, even in non-uniform circular motion. If I have time, I'll make a supplementary video that shows the derivation of this, but it will definitely be supplementary. Only watch it if you want to see how to use some interesting math to show this. I'm going to close up this video by introducing some useful equations. So remember the equations of uniformly accelerated motion way back near the beginning of the course. And these apply for uniform or constant acceleration, where I'll note that there's this relationship between the x component of velocity and the x component of position, and the x component of acceleration and the x component of velocity. Well, we have relations exactly like this. We're now talking about an angle and an angular velocity and an angular acceleration, and these are related to each other in exactly the same way. And so if the angular acceleration is constant, it then stands to reason that we'll get a set of equations just like these. And you do. In fact, all you need to do is essentially replace every v with an omega, and every a with an alpha, and every x with a theta, and you get the equations of motion for motion with uniform angular acceleration.